5.3 is quite long, but not quite difficult. Let's go ahead and take a look at it. A 5 kg box moves up an inclined plane AB at a constant velocity of 1.2 meters per second when a force F is applied. 5.1, let's calculate the magnitude of the force F if the power that is used to move the box up the incline AB is equals to 57.6 watts. So what is the information we have? We have the power. It is said to be equals to 57.6 watts. We are looking for the force. We have the average velocity, the constant velocity. I mean, we have V being equals to 1.2 meters per second. So how can we find the force with these three variables? You just need to recall that the power average is equals to the force multiplied by the average velocity. So what is the power? That is 57.6. What is the force? That's what we're interested in. Multiplied by the average velocity. In our case, it is constant. It is just 1.2. So that will be our average. We just need to divide both sides by 1.2. And if we do that, we get a force that is equals to 48 newtons. That is 5.1, quite straightforward. Let's take a look at 5.2. 5.2, we're supposed to state the work energy theorem in words. The net work done on an object by a net force is equals to the object's change in kinetic energy. That is 5.2. 5.3, the box now slides down slope BC. If the coefficient of kinetic friction of slope BC in the diagram above is 0.25, calculate the velocity of the block at point C by using energy principles only. So if the question says using only energy principles, there's three formulas you can use. You can use work net, you can use work done by non-conservative forces, and then you can use the conservation of mechanical energy. Well, the only way you would use the conservation of mechanical energy is if the only force that is acting on the object is force of gravity. If that is not the case, we cannot use the conservation of mechanical energy. So now we're left with work net and work non-conservative. Let's write the information we have down and see which formulas we need to use. We have the coefficient of kinetic friction. It is 0.25. We have our angle theta, which is equals to 32 degrees. We have our height, which is equals to 1.6 meters. What else do we have? Obviously, from the height and our angle theta, we can find the length of our incline. We can easily see that sine of 32 is equals to the opposite, which is our height divided by our hypotenuse BC. So BC is just equals to 1.6 divided by sine of 32. Let's see if we can use work non-conservative. So this will be equals to the change in kinetic energy plus the change in potential energy. Which non-conservative force is acting on our object? It is frictional force. So the work done by friction will be equals to Fr multiplied by delta X multiplied by cos of 180. So what is Fr? Fr will be the coefficient, which is 0.25 multiplied by the normal force. The normal force on an incline is mg cos of theta. So we're going to have 5 multiplied by 9.8 multiplied by cos of theta. Theta is 32. This is just the frictional force. Now we need the delta x. Delta x, as we have calculated above, it is 1.6 divided by sine of 32. Then everything multiplied by cos of 180. This will be equals to minus 31.3666. That is the work done by the frictional force. If we substitute it back into our equation, we're going to get minus 31.3666 being equals to the change in kinetic energy. So that will be a half. The mass is 5 kgs multiplied by Vf squared minus a half. The mass is 5 kgs multiplied by Vi squared. Our object was moving at a constant velocity of 1.2 meters per second. Potential energy final will be the mass 5 kgs multiplied by 9.8 multiplied by the height final at point C. That will be 0. The initial potential energy. The mass is 5 multiplied by 9.8 and then the initial height is 1.6. So minus 31.3666 will be equals to 5 divided by 2 Vf squared. So now we just need to add this term with this term. This will give us 0. If we do that, we're going to get minus 78.4. It is obvious what we need to do at this point. We need to take minus 78.4 to the left hand side. We're going to have 47.0334 being equals to 5 divided by 2 Vf squared. So Vf will be equals to the square root of 47.0334 divided by 5 divided by 2. Everything to the power a half. It's equals to 4.34 meters per second. 5.1. Define the term conservative force in words and give an example of such a force acting on block X. Conservative force is a force in which the work done in moving an object between 2 points is independent of the path taken, right? So that's the definition of a conservative force. And then now let's go to the example of such a force acting on block X. So in our context, in our scope, we only talk about one conservative force, which is the gravitational force of gravity, or the weight, right? So here we're gonna have force of gravity. And 5.2 is saying let's draw a free body diagram indicating all the forces parallel to the incline on the block. So let's go through our statement so that we can see what is happening. So we have block X of mass 4 kg, which is initially addressed at the bottom of an incline, which makes an angle of 25 degrees with the horizontal. A 78.4 newtons force acting parallel to the incline pulls the block X up the incline. Block X experiences a constant frictional force of 13 newtons. Right, so we are interested on the forces acting parallel to the incline. We know that we have a force applied, which is 78.4 newtons, and then we have a frictional force. Another force, which might not be obvious to some, is Fg parallel, right? Because we know that we're going to have weight going down, and then we can resolve that to the perpendicular component and the parallel component. And then if we do that, then we're going to have another force here, which is weight parallel going down the incline. So we have Fg parallel, right? Fg parallel is always going down the incline. So that is what we asked you to do in 5.2. And 5.3, using energy principles only, calculate the speed of block X after it has moved 3 meters up the incline. Right, so let's look at the information we have and see how we can approach this problem. So we have the magnitude of force applied, we have the magnitude of the frictional force. We can determine Fg parallel, right? So we can say that we basically have F net, right? And then we have delta X because we want the speed after the block is moved 3 meters. And then we have Vi because we study interest, right? And then we're looking for Vf. Yeah, I think that's all we have, right? From the information we have, which formula can we use under energy principles, right? So we can say that the work net is equals to the change in kinetic energy, right? But then we know that to find work net, we can also say F net multiplied by delta x multiplied by cos of theta is equals to a half mvf squared minus a half mvi squared. So let's go ahead and find f net. So we can say that f net is equals to, so we have the force applied minus the frictional force minus FG parallel, right? We're doing all that so we can find the F net. So force applied, it is said to be 78.4, and then the frictional force is 13 newtons, right? Now we need to find FG parallel. The formula for FG parallel is mg sine of theta, right? So what is the mass of our object? That is 4 kgs multiplied by 9,8 multiplied by sine of 25, right? So if we put that in our calculator, we should be able to find F net. So let me just do that real quick so that we can see what we have here. So sine of 25, so our F net is equals to 48.8334 newtons, right? So now we can go ahead and substitute in our equation and solve our problem. So F net, we say that F net is 48.8334, and then delta x, that is 3, right? And then cos of 0. Why am I saying cos of 0? So F net is positive, right? So that means that it is going up the incline, and that's where our displacement is. So the angle between F net and our displacement is 0, right? And that should all be equals to a half, the mass is 4 kgs, and then Vf squared minus a half 4 kgs, and the initial velocity, we're coming from rest, right? So that should be 0. We square that, and yeah, now we just need to solve for Vf squared. You know, the physics is essentially done here. We're just solving the math. So we're gonna have 146.5002 being equals to a half multiplied by 4, it will be 2, right? 2 Vf squared. So now it's easy to see that Vf will be equals to 146.5002 divided by 2 to the power half, right? We're dividing both sides by 2 and taking a square root on both sides. You know, it's the same as just taking something to the power half. And if we do that, we're getting a Vf of 8.56 meters per second. It is a force in which the work done in moving an object between 2 points is dependent on the path taken. So that is 5.1, a non-conservative force, right? And then 5.2, let's use energy principles to calculate the speed of the crate when it reaches point C. Right, so let's see what's going on here. We have an electric motor that pulls a 20 kg crate from rest at point A, right, up the incline by means of a light inextensible rope. And then we can see that the incline makes an angle of 18 degrees with the horizontal B, C, and D are points in the incline plane. And then we can see clearly that the distance between A and B is 15.6 meters. Right, we are told that the motor exerts a constant force of 96.8 newtons parallel to the incline. And then there's a constant frictional force of 13.5 newtons. Right, so we're supposed to use energy principle. If the question says use energy principles, you can use work net is equals to the change in EK. Right, you can also use the work done by non-conservative forces equals to the change in EK plus the change in EP. Right, you can do that. So let's just go ahead and solve it using the first formula, right? I've actually solved it using both So if you try this formula, it should also work. Right, so if we use that formula, we're going to get f net multiplied by delta x multiplied by cos of theta when it goes to half mvf squared minus a half mvi squared. Right, so now we can find the f net so that we can find vf ultimately, right? So how can we find f net? Let's draw a free body diagram of the 20 kg block as it moves up the incline, right? So we have FG parallel, which is pushing the object down the incline. We have the frictional force, right? And then the force applied by the electric motor. We have the normal force, obviously, and we have the weight perpendicular, right? The normal force and the weight perpendicular are not going to do any work on the object. So we are interested on the force applied by the electric motor, frictional force, and FG parallel. So if we find the net force, then we're going to get the net force being equals to the force applied, which is 96.8, right? So we're going to have 96.8 minus the forces that are opposing, frictional force, that is 13.5, minus FG parallel. So FG parallel is mg sine of theta, right? So that is FG parallel. And then if we substitute that in our equation, the mass is 20 kgs, the acceleration is 9.8, and then multiply by sine of 18 degrees. So if we put that in our calculator, then F net should be whatever we get there, right? So let me just do that real quick so that we can see what we get. And then I think our F net should be equals to 22.7327 newtons. Right, so now we have F net, we can put it in our equation. So in place of F net, we now put in 22.7327. Right, and then in place of delta x, we have 15.6. And then the object is moving up the incline, and the F net is also pointing up the incline. So the angle in between those two should be 0, right? So we're going to have cos of 0 being equals to a half. The mass is 20 kgs multiplied by Vf squared minus a half 20. Velocity initial, our object is coming from rest, right? So multiply by 0 squared. Right, so let me just solve the left hand side. And 22.7327 multiplied by 15.6 multiplied by 1. What am I getting? I'm getting 354.6301 is equals to, so I have multiplied by 20, that will be 10, right? And then we have Vf squared, right? So if we apply a bit of algebra here and make Vf the subject of the formula, we're going to get the square root of 354.6301 divided by 10. Right, so now what is left, I just need to put that in my calculator, and our Vf is 5.96 meters per second. Right, that is 5.2. Right, let's move to 5.3. So 5.3 is saying that let's calculate the minimum average power dissipated by the electric motor to pull the crate from point A to point C. So if we want to find the power, it's either we can use the work divided by the time, or we can use the force multiplied by the average velocity. Right, we don't have the time as it is, right? Maybe we can try calculate the work, but we don't have the time. But then if you look at the other formula, we have the force, right, that is exerted by our electric motor, right? And then we have Vi, which is equals to 0, and we have VF, which is equals to 5.96. So we can add those two and divide by 2 to find velocity average. Right. So what am I saying? I'm saying that the power will be equals to, so the force that is exerted by our motor, that is 96.8 multiplied by velocity average. So I'm saying to find velocity average, I'm going to say VF plus VI divided by 2. So what is VF? VF is 5.96 and then plus 0 divided by 2. Right. So that is 96.8 multiplied by 5.96 plus 0 divided by 2. And then the answer I'm getting here is 288.46 for, what is the SI unit of power again? I think it's watt. Right, so we're gonna have that there. I'm so much interested in how other people solved this problem, so please just let me know in the comments what you did for 5.3. Then 5.4 is saying that when the crate reaches point C, the rope breaks. So our rope is breaking at this point, at C. And then what happens next? The crate continues moving up the inclined plane, as you would expect. It comes to a stop at point D, and then slides down the plane past point B. Right. Draw a labeled free body diagram for the crate as it slides down the plane past point B. Right, so it's sliding down, and we need to draw a free body diagram for that motion. So when it is sliding down, FG parallel is still down the incline. FG parallel is down the incline. And then the frictional force is now up the incline. Right, and then we have our normal force there, and we have our weight perpendicular, or FG perpendicular, right? So I'm expecting 1, 2, 3. I'm expecting this question to be out of 3 marks because we have identified 3 forces, right? And indeed it is, right? So now I'm convinced that I have the correct free body diagram because my number of forces correlates with the marks for the question. Right, and then 5.5, let's look at what 5.5 says. So in 5.5, let's do a velocity time graph for the entire motion of the crate, starting from point A until it passes point B, and again on its motion down the inclined plane. Right, well, so we studied that V is equals to 0. And then at point B, we have, not at point B, but at point C, we have a velocity of 5.95 meters. So let's write 5.95 here. And then, right, let's have our VT graph. Yeah, so there we go to 5.95. And then what happens after we reach a velocity of 5.95? So the rope breaks, and then when the rope breaks, we no longer have that force that is pulling our object, but then our object will go up for some time before it reaches a VF of 0, right? As it is going up, its velocity is decreasing until it reaches 0, right? So let's see if we can indicate that in our graph. So it decreases until it reaches V is equals to 0, right? That is, now we at point D. We have reached V is equals to 0 because it's going to be increasing bit by bit until we reach V is equals to 0. And then after that point, now it is going down, right? Our object is going down and its velocity is starting to increase, right? So I'm thinking that we're going to have, something like this. Its velocity is starting to increase now. Alright, so I'm thinking we're gonna have something like that until we reach point A again. We don't know the velocity of point A. I don't think we need to indicate the value anyway. Right, I'm quite interested on how yours look like. Can you please just let me know in the comments if we have anything similar? Principle of conservation of mechanical energy. So it says that the total mechanical energy in an isolated system remains constant. So that is 5.1 state the principle of conservation of mechanical energy in words. And then now moving to 5.2, the question states that use the principle of conservation of mechanical energy to calculate the speed of the box when it reaches point Q. So let's go through our question statement so we can see what is going on. So we have a 2 kg box that is released from rest at point P. As we can clearly see here on the left hand side, it's released 5 meters above the ground, right? We have a height there of 5 meters. It slides down a smooth frictionless curved track PQ, as we can see on the diagram below, right? And then we are looking for the speed of the box at point Q. So we're interested in the speed at this point at Q. So let's jot down the information we have so that we can use the principle of conservation of mechanical energy to determine our answer. So this is at the top, right? When our box is at point P. When it's at point P, we know that VI is equals to 0 meters per second because it's been released from rest. And then we can see the height clearly, that the height is equals to 5 meters. And then now let's go at the bottom, or at point Q, right? So at point Q, the speed there is what we are looking for, right? And then we know fully well that the height is equals to 0 at point Q, right? So the principle of conservation of mechanical energy, it says that EP plus EK at the top is equals to EP plus EK at the bottom, right? So let's go ahead and calculate EP and EK at the top. We know fully well that EP is equals to the mass multiplied by gravity multiplied by the height, you know, for the faint-hearted ones. And then EK is equals to a half mv squared, right? Yeah, I'm just writing that down so that, you know, if you're not already familiar with the topic, you're not confused with what is going on. So EP at the top, we're gonna have the mass, which is 2 kgs, and then multiplied by the gravity, which is 9.8, multiplied by the height, which is 5 meters, and then plus EK. So EK is a half. The mass is 2 kgs, and the velocity at the top is equals to 0 because our object is sliding from rest. And then this will be equals to EP at the bottom. So EP at the bottom, we have the mass 2 kgs multiplied by 9.8 multiplied by 0, right? Because at the bottom the height is equals to 0, and then plus a half. The mass is 2 kgs, and then VF squared, right? We're looking for the velocity or the speed at the bottom, right? So let me go ahead and, you know, solve the left hand side so I can see what we have there. So we have 98 being equals to, and then if I put this here in my calculator, I'm gonna get 0, right? Because, you know, we're multiplying a few numbers by 0, so that should just give us 0. And then if we go ahead and solve this, so we have a half multiplied by 2, right? So that is 1. So we just have VF squared. So now what we're doing, we're essentially taking the square root on both sides, right? And then if you do that, we're gonna get VF is equals to 9.8994, meters per second. 9.5, not 4 by the way, meters per second. So that's the speed at point Q, right? Using the principle of conservation of mechanical energy. The reason why we're using this equation in 5.2 and why it works is because there's no friction, right? So let's put that in mind, that we can only use this equation when our system is isolated. And then let's move ahead and go to 5.3. So 5.3, we have a statement there saying that the box passes point Q and moves 10 meters on a rough horizontal surface before striking a barrier at point R at a speed of 4 meters per second. And then the question itself is saying that let's use energy principle to calculate the magnitude of the average frictional force acting on the box as it moves from Q to R. Right, so let's jot down all the information we have so that the information can guide us on which formula we need to use, right? Because we just don't pick a formula randomly. We have to be guided by the variables we have. So this speed that we calculated in 5.2, which is the velocity at Q, right? So for our motion from Q to R, that speed is going to be VI. Right, even though from P to Q is VF. So we're gonna have VI being equals to 9. So it's basically 9.9, right, meters per second. And then we have VF being equals to 4 meters per second. And then we have delta X being equals to 10 meters, right? And then the last thing, actually the key to the equation, is realizing that when the object is moving from Q to R, there's only one force that is doing work on the object, right? So let me show you. The object is here at Q and it's moving towards R, right? Obviously we're gonna have some normal force there, and we're gonna have some weight, right? And then there's no applied force whatsoever. There's only frictional force, right? So F net in our case is just frictional force, because that is the only force that is acting on our object as it moves from Q to R. So we have also F net, which is equals to the frictional force, right? So with these variables we have, we can use the work energy theorem, right? We can say that work net is equals to the change in EK. We can also use work done by non-conservative forces is equals to the change in EK plus the change in EP, right? All these formulas can work, right? I'm gonna use the first one. You guys can use the second one, and see if we're gonna get to the same answer. I know we are, but convince yourself. So work net, we know that it is equals to F net multiplied by delta X multiplied by cos of theta, and this is equals to a half mvf squared minus a half mvi squared, right? So if we go ahead and substitute, we've already established that F net is just frictional force, right? That is the only force that is doing work on our object. So we're gonna have Fr multiplied by 10 multiplied by cos of 180, right? The angle we use when we with regards to frictional force, it's always going to be 180 because it's opposing the motion parallel to the surface all the time. So yeah, the angle for frictional force is always 180. And then we have a half, the mass is 2 kgs, and then VF, we're given VF, right, 4 meters per second. So we have 4 squared and then minus a half, the mass is 2 kgs, and now VI, we've already established that it's 9.9, right? So we're gonna have 9.9 squared. On the left hand side, we're gonna have minus 10 frictional force, and now all we need to do is just solve the right hand side, and we are essentially done with the equation. So if we solve the right hand side, we're gonna get minus 82.01, and then if we divide that by minus 10 in attempt to find FR, we're gonna get the frictional force being equals to 8.2 0.201 newtons. Right, so that is 5.3. Let's move to 5.4. If there's any questions, there's any ambiguity, you gotta let me know in the comments. So 5.4, the barrier exerts an impulse of 14 newton seconds to the left on the box when the box strikes the barrier. Calculate the change in kinetic energy of the box after striking the barrier. Right, so if we need the change, we need some VF and VI, right? So VI is the velocity at which the box strikes the barrier, right? It strikes the barrier at a velocity of 4 meters per second. We have that in 5.3, right? It's right here. So we need VF, the velocity immediately after striking the barrier, right? But then how can we find that? We can find that using the impulse we're given, right? Because we know fully well that the impulse is equal to m VF minus VI, right? The impulse is said to be 14, right? But to the left, let's remember that to the left. So we're going to substitute that with a negative sign. So we're going to have minus 14 being equals to the mass of the object, which is 2 kgs. We're looking for VF, and VI is 4 meters per second, right? So we're going to have minus 14 being equals to 2 VF minus 8. Minus 14 plus 8 will be minus 6, being equals to 2 VF. It is easy to see now that VF is equals to minus 3 meters per second. So that is 3 meters per second to the left, right? So let's go ahead and find the change in kinetic energy. We know fully well that it is going to be equals to a half mvf squared minus a half mvi squared. So we're going to have a half, the mass is 2 kgs, vf is minus 3, right, squared, minus a half, the mass is 2 kgs, and vi is 4 meters per second. And then now it's just a matter of putting that in the calculator. Minus 7 joules, right? Minus 7 joules. This is laziness, if I can say, more especially because this same problem was in the June examination. But anyway, let's see what is happening. So we have a pulley system with a mass piece operated by an electric motor. It is used to lift a load of 120 kgs. Look at this. The load is said to be 120 kgs, and on the diagram, it is 125 kgs. Do you see what I'm talking about? Okay, cool. Vertically upwards at a constant speed, as shown in the diagram below. So they're moving at a constant speed. The load covers a distance of 6.8 meters in 0.01 seconds. Neglect all effects of friction. The first question, 5.1, defining what's the term power as applied in physics. That is the rate at which work is done. Power is the rate at which work is done. Let's move to 5.2. Calculate the work done by the gravitational force on the load. So what am I supposed to use now? Am I supposed to use 125? Am I supposed to use 120? It's just a mess. Okay, fine. The work done by gravitational force is equals to the force by gravity multiplied by delta y cos of theta. So let's go ahead and substitute. Fg is equals to the mass. Let's take 125 multiplied by the gravity, which is 9,8. Delta y, it covers a distance of 6.8 meters. So we have 6.8 multiplied by cos of theta. Well, gravity is acting downwards, obviously, but the load is moving upwards. So we have an angle of 180 degrees. If you put that on your calculator, you're going to get minus 8,330 joules as the work done by the gravitational force on the load. And now, 5.3. Determine the average power output required by the electric motor to lift the load through 6.8 meters in 0.01 seconds. So the key takeaway here is the fact that they are moving at a constant velocity. So we can set up our equation in the following ways. Work net is equals to change in EK. If it is constant velocity, then change in EK is obviously going to be equals to 0. But let's look at the forces that are acting on the system. We have the work done by gravitational force on the load, and we have the work done by the motor. The mesh piece is doing positive work. It is going down, and there's gravitational force on it that is also going down. So the work there is positive. We can set up our equation in the following way. The work done by the motor plus the work done by the mesh piece plus the work done by Fg on the load is equals to 0. We want the work done by the motor. We have the work done by Fg on the load. We just need to find the work done by the mesh piece. Let's find the work done by the mesh piece separately. The work done by the mesh piece will be equals to F, which is gravitational, 100 multiplied by 9.8. The distance covered, 6.8, and a cos of 0. We have already determined that the mesh piece is doing positive work. We're going to get 6,664 joules. Now, if we substitute back in our equation, the work done by the motor plus 6,664 minus 8,330 is equals to 0. So the work done by the motor is equals to 8,330 minus 6,664. You're going to get 1,666 joules. This is the work done by the motor. But we're looking for the power. The power is the rate at which work is done. So we're just going to have 1,666 divided by the time, 0.01. We're going to have 166,600 watts. Conservative force, it is a force in which the work done in moving an object between 2 points is independent of the path taken. So that is 4.1, right? If we move to 4.2, the question is saying that let's name the conservative force in the diagram above, right? Without even looking at the diagram, I know that in our context, in our scope, we have only one conservative force, which is force of gravity or gravitational force. So the answer for 4.2 is force of gravity. That's the only conservative force we talk about in our scope. Moving to 4.3 is saying that let's take the work energy theorem in words. So we have work net being equals to the change in EK, and that in words goes as follows. The net work done on an object is equals to the object's change in kinetic energy. So the net work done on an object is equals to the object's change in kinetic energy. Basically, you just explaining the formula, right? Because it's easy to see from the formula that the net work done on an object is equals to the object's change in kinetic energy. 4.4. So 4.4 is in that the velocity of the block at point B is 6.92 meters per second. So at this point we have 6.92 meters per second, right, at point B. And then the question goes on to say that use energy principles only to calculate the frictional force that the block experiences and it moves from point A to point B. So when the question says let's use energy principles, there's two equations we can use. Work net is equals to the change in EK, and then work done by non-conservative forces is equals to the change in EK plus the change in EP, the potential energy, right? So I'm gonna go ahead and use the second equation to answer our problem, and then you guys can use the first one so that we can see if we end up at the same answer. So let me go ahead and do that, right? But then before I answer any question, I have to draw a free body diagram, right? So that I can see clearly what is going on. So if I go ahead and do that, so the block is going down. As it is going down, we know that there is the weight, which we can resolve to weight parallel and weight perpendicular, right? And then we have the normal force, and we have the frictional force, right? So if you look at the forces acting parallel the surface, we have the frictional force and weight parallel, right? But then we know that force of gravity is conservative, right? So if I'm using the second equation, which says that the work done by non-conservative forces, then the only force I will consider is friction, right? So if I go ahead and do that, I'm gonna have frictional force multiplied by delta x multiplied by cos of theta, right? So that is supposed to be equals to the change in EK plus the change in EP, right? So if we go ahead and compute that, we're gonna get a half mvf squared minus a half mvi squared, and then plus mgh final minus mgh initial, right? And if we go ahead and substitute, friction is what we're looking for, so we're just going to have fr then, and then multiply by delta x, which is equals to 8 meters, right? The displacement of the object, and then multiply by cos of 180. When you're calculating the work done by friction, it will always be cos of 180 because it always acts in the opposite direction. And then that will be equals to a half. The mass of the object is 2 kgs. And then velocity final, it's here, right? We've talked about it, 6.92. So we have 6.92 squared minus a half the mass of the object, which is 2, and then velocity initial, which is 2 meters per second, right? We square that, and then we have plus mgh final. So the mass is 2 kgs. And then g, gravity, is 9.8, and then the height final. So now we have a problem. We need the height in order to use that equation, and we don't have it, right? So let's look here. We need that side. Yeah, we need the height. So what we have an angle and the hypotenuse, right? So it's easy to see that we can go ahead and say that. Let me just do it here real quick. Sine of theta is equals to the opposite, which is our height, right? Divided by the hypotenuse. So we're gonna have sine of 30 being equals to the height divided by 8. So the height is equals to 8 multiplied by sine of 30, which is equals to 4. So our height is equals to 4, right? So let's go ahead and solve our problem. So here we're gonna have so the height final. So we're coming from a height of 4, right? And then we go in here at B where the height is 0. So the height final is 0, and then height initial is the one that is equals to 4, right? So we're gonna get minus 8 frictional force is equals to, and then if you compute the right hand side, you're gonna get minus 34.5136, and then if we divide both sides by minus 8, so let's just go ahead and do that. Dividing both sides by minus 8, we're gonna get the frictional force being equals to 4.31 newtons. So that is 4.4, right? Let's do 4.5 real quick. So 4.5. The question is saying that the coefficient of friction for the last horizontal stretch after point B is 0.35. So here we have a coefficient of 0.35, right? And then the question says that let's calculate the distance the block will travel before coming to a complete stop without using equations of motions. So if it is coming to a complete stop, then we know fully well that we have VF is equals to 0, right? But then that's not all we have. We also know that VI is equals to 6.92 meters per second for that part of the motion. Yeah, it was VF from point A to B, but then from point B to a complete stop, it is now VI, right? And then what else do we have? We have the coefficient, which is equals to 0.35. So let's go ahead and set up our equations and see what we can do here. So we can use work net is equals to the change in EK, and we are governed by the variables you have, right? If you have VF and VI, you're most likely gonna use this equation or that other one. So we're not just choosing it in randomly, we are guided by the variables we have. So now all we have to do is draw a free body diagram for the object. You're gonna see real quick that the only force acting is frictional force, right? Because even though the weight is acting on a flat surface, it does zero work. We have the normal, it always do zero work. So we're gonna have the work net being the force done by friction multiplied by delta x multiplied by cos of theta being equals to a half mvf squared minus a half mvi squared. So the frictional force will be the coefficient multiplied by the normal force. We know that fully well, right? So the coefficient is 0.35 and the normal force is mass multiplied by gravity. So that will be 2 multiplied by 9,8, and then we have delta x, and then the angle that we have there is obviously cos of 180, right, for frictional force, and that should be all equals to, so I'm running out of space, so I'm just gonna write it here. So that should all be equals to a half, the mass is 2 kgs, and velocity final, we know that it is 0 if we go into a complete stop, right? And then minus a half, 2 kgs, and then the initial velocity is 6.92 squared, right? So now all we need to do is just solve the right hand side and look for delta x, right? So if you do that, you're gonna get minus 6.86 multiplied by delta x is equals to the right hand side. So let me just put that in my calculator real quick and see what I get here. So I'm getting minus 47.8864, and then it is easy to see that we're going to divide both sides by minus 6.86, right? And then if we do that, we're gonna get delta x being equals to 6.98 meters. Free body diagram for the load while it moves upward, that is 5.1, right? So let's read through the question statement so that we can see what is happening here. So a load of mass 75 kg is initially addressed on the ground. It is then pulled vertically upwards at a constant acceleration of 0.65 meters per second squared by means of a light inextensible rope. Refer to the diagram below, ignore air resistance, rotational effects, and the mass of the rope. Right, so our free body diagram. So our object is being pulled vertically upwards, right, by means of a rope. So we're supposed to have tangent force pointing upwards. So we have tension there, right? And then going down, it is not talked about, but we know fully well that gravitational force is always acting on any object of interest, right? So we're going to have the weight there, or you can put Fg. That's totally fine. And then the question that follows, 5.2, it says that let's name the non-conservative force acting on the load. So we have two forces acting on the load. We have the weight and the tension force. Like I've said on other videos, the only conservative force in our context, in our scope, is the weight. Any other force is non-conservative. So the answer for 5.2 is the tension force, right? Tension force. If we had applied force, it would be the applied force. If we had any other, it will be that force. Our only conservative force is the weight. Everything else is non-conservative. Right, let's move to 5.3. So 5.3 is saying that let's calculate the work done on the load by gravitational force when the load has reached a height of 12 meters. So when it has went up 12 meters, right? So let me just show you something here, right? Let's go back to a free body diagram. The object has went up 12 meters, right? And then the weight is going down. The weight is going down, as we can all see, right? So the angle between the displacement and the weight is 180 degrees, right? I just wanted to make that clear before we do any other thing. So now we can go ahead and say that the work done by Fg is equals to Fg delta x cos of theta, right? And this will be equals to, so what is Fg? We know fully well that Fg is the mass multiplied by gravity. So we're going to have 75 multiplied by 9,8, all right? And then now we're interested in the displacement, which we know fully well that it is 12 meters. And then now cos of 180 degrees. The object is going up, gravity is pointing down. So gravity is supposed to be doing negative work on the object, right? Because it is not in the same direction as the displacement. And then if you put that in your calculator, you will indeed get minus 8,820 joules, right? Which is what we're expecting. We're expecting the work done by gravity to be negative, as it is pointing in the opposite direction to the displacement of the object. And moving right through 5.4. So 5.4 is saying that let's take the work energy theorem in words. So we know fully well that work net is equals to the change in EK, right? And that in words would say that the net work done on an object is equals to the object's change in kinetic energy. It's easy to see that the work net, or the net work done on the object, is equals to the object's change in kinetic energy. Right. 5.5. Use the work energy theorem to calculate the speed of the load when it is at a height of 12 meters. Right. So for this kind of questions, we have to write down our information so that we can be guided on which formula to use, right? So we have our delta x, which is equals to 12 meters. And then we have our VI, which is equals to 0 meters per second, because our object is coming from rest. And then VF is what we're looking for. What else do we have? We have an acceleration, which is given to us, of 0.65 meters per second squared. And then we have a mass of 75 kgs, right? But then I think here the key to this question, depending on which approach you use, right, is realizing that we have the mass and the acceleration. So we essentially have F net, because we know that F net is equals to ma, right? So now we can say that work net is equals to the change in EK. Now I want to point something interesting to you. Look, at 4.4, the question is saying that, at 5.4, the question is saying that, let's state the work energy theorem in words. And then in 5.5, we're using the work energy theorem. So always be, aware of these things, that if a question asks you to define something, you're probably going to use that law, right, to answer the questions that probably follow. Right, let's get on with the question. So for work net, we can put F net multiplied by delta x multiplied by cos of theta being equals to a half mvf squared minus a half mvi squared. Right, so what is F net? We've already established that F net is equals to ma, right? So in place of F net, we can just put that the mass of the object is 75, and then the acceleration is 0.65. Delta x, we know fully well that it is 12, and then cos of theta. So what is theta? Let's look at F net, right? We have 75 multiplied by 0.65. The product of two positive numbers is positive, right? So that means that F net is pointing up. It is positive, right? So F net is going up. We know that our displacement is also upwards, so the angle between the F net and our displacement is 0, right? So we're gonna have cos of 0 there, and then that will all be equals to a half. The mass of the object is 75, so 75, and then VF is what we're interested in, so we have VF squared minus a half 75. Vi is 0, we're coming from rest, so we have 0 squared, right? Yes. And then now we essentially done with the physics. We just solving for VF squared, right? Now we just have to do the math essentially. So on the left hand side, we have 585, and then it's supposed to be equals to 75 divided by 2 VF squared, right? And then it is easy to see now that VF will be equals to 585 divided by 75 divided by 2, and everything to the power a half, right? That's the same thing as taking square roots on both sides, and then we get VF being equals to 3.95 meters per second.